Now, last time we were looking at seismic waves in relation to earthquakes, but today we're going to see how seismic waves also allow us to study the interior of the Earth. Now, most of our knowledge of Earth's interior comes from the study of earthquake waves, but in particular, the travel times of P waves and S waves as they pass through the Earth will vary depending on the properties of the materials. And these variations in the travel times correspond to changes in the materials that are encountered. Here, for an example, we have an earthquake source, and seismic waves are radiating from the source as a series of wave fronts. Well, we can follow these wave fronts as they pass through Earth's interior by constructing what are called seismic rays. The seismic rays originate at the source of the energy and are constructed perpendicular to the wave fronts. And there's an infinite number of seismic ray paths that can be constructed, and what we're going to do is just simply follow one or two of these paths and see how the seismic energy changes as it passes through deeper parts of Earth's interior. And that's shown again in this figure. Notice that when traveling through the Earth, these seismic waves spread out from the earthquake source, the hypocenter, as circular features called wave fronts. And the path of these waves can be also considered seismic rays, such that we can draw lines perpendicular to the wave fronts, as shown in this figure. Here is a cutaway view of Earth's interior showing the ray paths of direct seismic waves that pass through Earth's mantle. By direct, we simply mean that the ray paths passed through the mantle and emerge back on the surface at some other location. So seismic waves emerge from the hypocenter, also known as the focus, and travel through the Earth along these bent paths. And eventually these waves are recorded by distant seismograph stations. And by noting the character and travel times of the seismic waves, we can derive important clues about the overall makeup and composition of Earth's interior. The bending of seismic waves while passing through the Earth is referred to as refraction. Here, for an example, we have a fishbowl that's partly filled with water. And notice the path of one particular laser beam as it passes through the air within the upper part of the fishbowl and encounters the boundary between the air and the water. The ray will cross that boundary and enter the water, but notice that its path has been bent downward as a result. And this bending of the ray when passing through different material is what's referred to as refraction. Another ray path, on the other hand, is reflected off that boundary and returns to the original medium, in this case the water. And this is the behavior of seismic waves. They can undergo both refraction and reflection when passing through deeper parts of the Earth's interior. So here we have a block diagram showing two different rock types. Rock type 1 occurring as the upper layer, and then the lower layer is identified as rock type 2. And here we're following a particular ray path as it passes through Earth's crust. And notice that when the seismic rays, or in this case waves, encounter a boundary between materials with different properties, the energy splits into both reflected and refracted or bent waves. The refracted wave continues into rock layer 2, but notice that its path has been bent in the process. And the way this bending occurs depends on whether the rock layer 2 speeds up the seismic waves or slows down the seismic waves. Now, when the velocity of the seismic wave increases when passing from one layer into another, the waves will refract or bend upward towards the boundary separating the two layers. So in this particular example, the seismic waves speed up, increase in velocity when passing from rock layer 1 to rock layer 2, and as a result, the refracted wave bends upward. Does everybody see this? We're following one particular ray path in going into the interior. So in other words, it's going from slower to faster velocity when passing from rock type 1 to rock type 2, and as a result, the ray path bends upward as a result. Alternatively, when the velocity of seismic waves decrease when passing from one layer into another, the waves refract or bend downward away from the boundary separating the two layers. So in this case, the seismic velocity goes from faster to slower when passing through rock type 2, and as a result, that ray path will bend downward. Okay. Now, P waves bend outward when passing through the mantle, and this is due to an increase in velocity with depth. Now, the increasing velocity with depth within the mantle is simply due to increasing mantle density with depth. As the density of the material increases, the velocity of the seismic waves tend to increase as a result, and this causes the overall bending outward or upward of the different ray paths when passing through Earth's mantle. And we see that seismometers on the surface, particularly seismometers located between the earthquake and about 100 degrees within that particular quadrant, will therefore record direct P waves as they emerge on the surface. Now notice that P waves bend downward when entering the outer core, and this is due to a decrease in the velocity of the seismic waves. And the P waves will then bend outward again when they leave the outer core and enter the mantle within the lower part of this diagram. The overall bending of P waves when passing through the outer core creates what's called a P wave shadow zone. And in this particular figure, the P wave shadow zone occurs between quadrants of 100 degrees and 140 degrees. And basically what this means is that seismograph stations located anywhere between 100 and 140 degrees, in other words, within the P wave shadow zone, will not record P waves whatsoever. And this is entirely due to the slowing down of these seismic waves when passing through the outer core. Now, S waves, as we saw before, cannot travel through liquids. And therefore, because the outer core is liquid, S waves will not pass through it. And as a result, the S wave shadow zone is much larger than that of the P waves, stretching from quadrants 100 degrees on the right all the way around to 100 degrees on the left. And what this means is that seismograph stations located on the surface anywhere within the S-wave shadow zone will not record S-waves. So here's a summary diagram showing both the paths of P waves and S waves. The P waves are indicated by the black ray paths, whereas the S waves are indicated by the red ray paths. Now, for this particular seismic station that occurs outside of both shadow zones, notice that the seismic station records both P and S waves within this particular location. Further down, we have a seismic station that occurs inside both P wave and S wave shadow zones, and as a result, neither of these waves are going to be recorded. And the last example at the bottom is for a seismic station outside the P wave but inside the S wave shadow zone. And as a result, this station is going to record P waves but not S waves. Now, the characteristics of these different seismic wave patterns in different parts of the Earth is the main piece of evidence that tells a seismologist that the outer core must be liquid, because it slows down P waves and at the same time does not allow S waves to pass through it. Okay? Now seismic waves can also reflect when reaching the boundary between two different materials. And so, for example, the reflected waves shown in this particular diagram, one of these reflected waves is the result of bouncing off the boundary between the lower mantle and the outer core. And the second reflected wave has bounced off the boundary between the outer core and the inner core. And this reflection in turn will then return these waves to the surface where seismograph stations located within that particular region will record them. We can also get what's called a double reflection. Here, from the earthquake source, we see that one direct wave, P wave, will bounce off the surface and pass into the mantle again and then return to the surface as a double reflection. And a seismograph station located at that point will record that particular ray path. Here we see a snapshot. This is a computer simulation of S waves following a earthquake. And these values are in terms of seconds, increasing from top to bottom. And we see that in actuality, seismic waves not only refract, they also reflect when passing through Earth materials. Reflected seismic waves are used in the search for underground oil and gas reserves. And in this case, seismologists go out into the field and they set off these explosive charges in order to generate artificial seismic waves. And then notice how each of these different ray paths bounce off or reflect off these different boundaries between layers. And then we have a series of seismographs that are positioned on the surface to record these various reflected waves. And then from there, the seismograms, the records are processed and used to image, or for the most part, kind of like a CAT scan, produce kind of an image or CAT scan of various geologic structures that have the potential for trapping reserves of oil and gas. We can define the structure of Earth's interior two different ways. We can define the layers simply based on the compositions or we can define the layers based on physical properties, in particular by noting how the behavior of seismic waves change when passing from one region into another region. Now, if we were to define the Earth's interior simply on the basis of composition, we'd only be able to distinguish a crust composed mainly of silicates, a mantle composed primarily of ultramafic rock, and a core consisting of iron. On the other hand, if we take into account the behavior of seismic waves, we can further define layers based on changing physical properties into such things as the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core. So here we see the Earth's layered structure based on physical properties. And beginning near the surface and considering crust, we can right away distinguish continental crust from oceanic crust. Seismic waves behave differently between these two materials. Below the lithosphere, we can identify a weak asthenosphere, and then deeper into the interior, we can distinguish a lower mantle called the mesosphere, consisting of solid rocky material. And then we can even distinguish an outer core from an inner core based simply on whether the iron is liquid or solid. As a result, this shows us that seismic waves are gives us a lot more information about Earth's interior compared to if we just considered the composition alone. Seismic waves can reveal the thickness of Earth's crust. As an example, here we have an earthquake source. If we look at this upper block diagram, we have this earthquake source indicated by this yellow star. And from there, we're going to follow two different ray paths. One ray path represents what's called the direct wave, which will go strictly from the source to the seismograph instrument. And we're also going to follow a second ray path, that of a refracted wave that passes deeper into the crust and actually encounters the boundary between the crust and the upper mantle. So let's begin by looking at Station 1, Seismograph Station 1. Now at Station 1, the direct wave, which travels slower, will still arrive at Station 1 before the refracted wave, which travels faster, simply because of the shorter path of the direct wave. And so let's move down to this bottom graph, which is a plot of time versus distance. And we see here that the point representing the direct wave will appear before the point representing the refracted wave. Okay? So there's a lag time between the arrival of the direct wave and the arrival of the refracted wave at this particular station. Now at seismic station 2, located further from the earthquake source, both the direct and the refracted wave arrive at the same time. And this is because the faster moving refracted wave, even though it travels a longer distance, will catch up with the slower direct wave and arrive at Station 2 simultaneously. And so if you go back down to this lower graph, the position of both the direct and refracted wave coincide. Okay? Further away at seismic station 3, here the faster refracted wave overtakes the direct wave and arrives first, even though it travels a longer distance. And we see this in the bottom graph where the refracted wave arrives before the direct wave. The net result is that the distance from the source where this crossover occurs, the crossover being the location of seismic station 2, this crossover distance can then be used to calculate the overall crustal thickness. Now, the seismic waves define what's known as the MOHO, which was discovered back in 1909. What was found was that the average velocity of P waves increased at a distance of about 200 kilometers from the earthquake source. And the conclusion was that at 50 kilometers depth, there was a change in the physical properties that marked the base of the crust. And the base of the crust, as a result, is now defined as the MOHO, which is abbreviated from the name of the actual discoverer. And I'm not about to make a fool out of myself and try to pronounce this name. Okay. So this is a time distance graph where the epicenter plots at the origin. Now, the location of seismograph station 1 is measuring the direct wave. In other words, the direct wave reaches seismograph station 1 first, and that point, that time and distance of seismograph station 1 where that direct wave arrives is plotted in that upper diagram. At a little bit further distance, at seismograph station 2, that station is also receiving the direct wave first, as is seismograph station 3 and seismograph station 4. Now, as we go further from the source, we then, at seismograph station 5, at 5, the refracted wave is arriving first. And the same thing for station 6. The refracted wave arrives before the direct wave. And as a result, notice that we can calculate the velocities of these two curves. These are simply time distance curves, so we can calculate the velocities from the slopes of these curves. And we see that the crust has an average velocity of about 6 kilometers per second. The average velocity of the upper mantle is 8 kilometers per second. And that deflection or bend in these two different curves marks the MOHO, or the boundary between the crust and the mantle. That distance of station 4 from the source can then be used to calculate the overall thickness of the crust. Now, as a result, seismic studies indicate that the crust varies significantly in thickness, particularly when you compare continental versus oceanic crust. And as we saw at the beginning of the semester, oceanic crust is quite a bit thinner, ranging from 3 to 15 kilometers thick, and consists primarily of basalt and gabbro, whereas continental crust is significantly thicker, ranging from 40 to 65 kilometers thick, and has the average composition somewhere around a granite. As a result, continental crust is less dense, more buoyant than oceanic crust. Now here's a cutaway view of the Earth, and here we're looking at two different curves, one for the velocity of P waves and one for the velocity of S waves. And the actual values for velocity are given on the scale at the bottom of this figure, ranging from 2 to about 16 kilometers per second. And notice that overall P waves travel about twice as fast as S waves. Now, where these white arrows are indicating on these curves, we see that seismic velocities increase abruptly below the crust. And we see that in both the S waves and the P waves, there's the curves kind of shift towards the right, towards higher velocities, where those white arrows are pointing. And this is due to a compositional change from crustal rocks to mantle peridotite, which is quite a bit denser. And so this allows us to define what's called the lithosphere, which includes the crust and the solid upper portion of the mantle. And we saw before that the lithosphere is a relatively cool, rigid layer averaging about 100 kilometers in thickness, but may be as much as 250 kilometers or more thick beneath older portions of continents. And it's the lithosphere that in turn is broken into a series of plates that define plate tectonics. Now, as we go a little bit deeper into the upper mantle, notice that seismic velocities decrease within the upper asthenosphere, and this is because peridotite contains a few percent partial melt, but not enough to completely stop S waves. And this defines the asthenosphere as a weak sphere located within the upper portion of the mantle directly beneath the lithosphere. And this region is also known as the low velocity zone because it slows down seismic waves. And this is due to a small amount of melt within the upper portion, which in turn mechanically detaches it from the overlying rigid lithosphere. And as a result, the solid lithosphere can be envisioned as moving over the and is partially decoupled from the underlying asthenosphere. And in the figure on the right, notice that the upper part of the asthenosphere is mainly softened peridotite. But as we go deeper into the asthenosphere, the peridotite becomes solid at depth, and is certainly solid by the time we reach a depth of around 410 kilometers below the surface. Now, as we go deeper, we encounter two transition zones, both marked by increases in seismic wave velocities as determined by both S waves and P waves. The shallower transition zone, located at a depth of around 400 kilometers depth, is where the mineral olivine changes into a spinel crystal structure of a higher density. And this is shown in this pop-up figure where the mineral olivine is relatively stable under lower pressures, but at a depth of 400 kilometers, pressures have increased to the point where olivine changes into a different crystal structure known as the beta spinel structure, which is quite a bit denser. And as a result, this accounts for the increase in both S waves and P waves. At the deeper transition zone, which occurs at a depth of around 660 kilometers, spinel changes to a higher density crystal structure known as perovskite. And that accounts again for the abrupt increase in both S waves and P waves at 660 kilometers depth. Below the 660 kilometer transition zone, we then enter the lower mantle, which is also called the mesosphere. And we see that in passing through the mesosphere, the velocities of both S waves and P waves increase with depth, telling us that rocks in the mesosphere, although solid, are also very hot and capable of gradual flow. And they have to be in order to convect, as we'll look at a little bit later in detail. It behaves ductily. Ductile deformation occurs in solids, but over time the solids will actually contort and change shape due to high pressures, high stresses, and so on. And that's referred to as ductile or plastic deformation. And that's what's thought to occur within the ultramafic rock within the mesosphere. Now, the D-double prime layer comprises the bottom few hundred kilometers of the lower mantle just above the outer core. And here, the D-double prime layer exhibits large horizontal variations in both temperature and composition as determined by seismic waves. The D-double prime layer is thought to be the possible graveyard of subducted oceanic lithosphere, and what's more, also constitutes the birthplace of some mantle plumes that originate at the mantle core boundary. And these plumes will then rise through the overlying mantle and eventually impinge upon the base of oceanic lithosphere, creating these hot spots, of which, again, the island of Hawaii tends to be a good example. Now, the outer core is thought to be composed of liquid iron. And the reason seismologists conclude this is because P waves dramatically slow down when passing through the outer core, and S waves cannot pass through it. So the outer core is the liquid iron layer, which is approximately 2,270 kilometers thick, and it's thought to be composed mostly of a liquid iron-nickel alloy. What's more, convective flow in the liquid outer core is thought to be responsible for generating Earth's magnetic field, and we'll look at this in more detail in the next lecture. The inner core is a sphere of radius with a radius of about 2161 miles or 3486 kilometers, on the other hand, composed of solid iron. And as a result, looking in the profile of seismic waves, we find that P waves speed up again. How can we get S waves within the solid iron inner core if it doesn't pass through the liquid iron outer core? This is a very good question. Yeah, P waves can change to S waves. So those S waves passing through the inner core actually pass through the outer core as P waves, and then change to S waves when traveling through the inner core. And then passing through the outer core again, they change back into P waves, and this is all determined by modeling the range of just the overall pattern of S and P waves recorded from all of these different seismograph stations. And some waves can be accounted for as being direct waves or reflected waves, but they got these other waves popping up within the pattern, the seismogram, that they can't really explain. So they try to do all these different modeling algorithms, and they finally come up with this idea that this peculiar wave signature on the seismogram seems to be a P wave, which changed to an S wave and back to the P wave again. And that's how they basically come up with these interpretations. It's very very complex mathematical modeling for the most. Let's see.